Hi everyone, we are from Group 7. I myself Gayatri and my team members' name is Durkashana Vashani, Jesslyn, Yengting and Uruswin. We are going to present about total hip replacement. I'm going to present about introduction and also Autocad part. Introduction. The hip joint is vital ball and socket joint that connects the femur to the pelvic acetylbulum and support body weight during movements such as walking. Damage to this joint due to the disease like osteoarthritis or injury can cause severe pain and limited mobility, often requiring total hip replacement surgery. In this procedure, the damaged joint is replaced with an artificial hip prosthesis designed to restore normal movement and stability. Modern prosthetic design use modular compounds and advanced material to improvise performance and durability. In this study, computer-aided design tools such as AutoCAD and Autodesk Inventor are used to model the hip processes while ANSI software is applied to perform finite element analysis to evaluate deformation, stress, strain under psychology loading condition with the aim of improving implants durability and patient outcomes. Now I am going to explain about the AutoCAD part. 2-dimensional, which is 2D drawings of the hip prosthesis created using AutoCAD 2026 version during the early stage of design process. The process of this design is to define the overall geometry, key dimension and important design features required for a functional hip implant. At this stage, the 2D drawing acts as a technical reference to ensure accuracy and consistency in the design. The main feature shown in 2D drawing is the femoral stem. The component is designed to be inserted into the femur to support the artificial hip joint. The stem has a smooth, curved profile that follows the natural anatomical shape of the femur. The curvature is important because it helps distribute the applied body load more evenly along the stem, reducing stress, concentration, and improving stability after implantation.
I'm going to explain about the upper part of the 2D drawing. The 2D drawing shows the spherical femoral head. The femoral head is designed as a true sphere to allow smooth articulation within the acetylbullar socket of the pelvis. Fillets are clearly indicated in the 2D drawing at critical junctions to reduce stress, concentration, and improve durability. A short cylindrical neck is shown connecting the femoral head to femoral stem to ensure proper alignment and structural continuity. Then, the picture represents multiple orthographic views of the prosthesis, including the front, top, side, and isometric views. These views are important in 2D drafting as they provide a complete representation of the prosthetic shape and dimension. By using these views, the overall geometry, orientation, and dimensional accuracy of the hip prosthesis can be clearly understood.
I'll be talking about the drawing on Inventor software. So I'll be talking about the 3D sketching and the design process. As for the first one, which is the initial profile and revolution, the process is actually begin with a 2D sketch centered on a circle with a radius of 16.5 millimeters. As for the second step, we are using complex, soft, and transition. Why using it? It's actually to replicate and the natural of the tapering form of the femur by using multiple sectional plane that were drawn along the length of the prosthesis. As for the third one is geometric guidance, that a center line sketch guide the overall form, while the angle is specific with the reference line at 77 degrees, 8 degrees, 21 degrees to control the transition between each section. For the fourth one, there will be seamless integration, that the lofting tool is actually used to join this section in order to maintain the tangency constraint as to ensure the transition was smooth and anatomically accurate. As for the fifth is refinement with fillet. The use of the fillets is as to improve the bone strength and the patient comfortability towards the hip prosthesis. That's why the fillet is applied. There were two fillets that were used. One is a large, one is a small. One is a large, one is a small. And the large radius were used is 2 mm, and the small radius is 0.5. The large radius is for the major transition, as the small radius is used for the small transition as to smooth out the remaining edge and in order to minimize the stress concentration. Thank you.
I am Kuhui and I was responsible for the volumetric modeling phase using Autodesk Inventor. Beyond the basic geometry, several critical design choices were made to ensure the implant clinical success. For the anatomical curvature, we chose a curved stem design rather than a straight one. Engineering literature on orthopedics emphasizes that the human femur is not perfectly straight. This is critical for correct anatomical positioning and ensuring that the body weight transfers properly after the surgery. And in the Autodesk Inventor 3D sketch and modeling process, the strategy use of the fillets is critical based on the mechanical design principles. We apply the larger 2 mm radius for major transitions and smaller 0.5 mm fillets to smooth out the edges. This is critical because sharp edges act as failure points under physiological loads. So it is critical design choice to minimize the stress concentration. This prevents the material from cracking at a single point under heavy loads, which directly improves the durability of the prosthetic. And the upper section features a true spherical head. For a ball and socket joint to function, the contact surface must be perfectly smooth and geometrically aligned. So, modeling a true sphere allows for proper contact with the pelvic socket. This reduces friction and wear over time, allowing the patient to have a smooth range of motion. And the choice to use lofting method rather than simple extrusions is a technical decision. I use the lofting tool guided by sectional planes at angles of 77 degrees, 8 degrees, and 21 degrees. The femoral stem must taper as it goes deeper into the bone to fit the hollow part of the bone. So using the lobes rather than extrusions creates a smooth and continuous transitions. This prevents sudden change in geometry that could irritate the bone or create weak points in the metal surface. And we also include a distinct triangular cutouts which extrude a 5 mm cut, and the triangular cutout is with 60 degrees angles. Professionals implants often feature specific cutouts to provide a firm fixation and long-term stability within the cortical bone. So these act as a functional feature to help the implant stay in close contact with the surrounding bone and providing a more secure fit.
Hi, my name is Jasmine Melchizedek with a matrix number of 251153619. And in today's presentation, I will be covering the later stages of the project, which starts from the ANSYS simulation setup, the patient file used, and also the materials that we use to compare the results, and also the optimization. So first off, when we start with the 3D modeling stage in the Autodesk Inventor, it is used to refine the hip prosthesis design. And in this stage, we mainly focus on making the implant anatomically suitable rather than just visually accurate. So the femoral stem that we designed has a gentle curvature and it follows the natural shape of the femur, which helps to improve the stability and the load transfer after the implant. So after finalizing this 3D model, we moved on to ANSYS software, which we use finite element analysis. And the main purpose of using ANSYS is to subject the digital prototype to simulate physiological loading conditions, especially weight-bearing forces experience like walking, running, and more on. So before running through the simulation, the model we had to go through a meshing process. So the geometry that we had provided is divided into smaller finite elements and it improves the accuracy. So the localized mesh refinement strategy is applied where the high stress region, such as the neck of the femoral stem, were assigned with a finer mesh with the size of 2 millimeters and remaining regions with a global mesh of 5 millimeters. So this ensured the accurate stress and the strain in the critical areas. So during the analysis, we can see the three key parameters that is evaluated versus total deformation, which is used to assess the stiffness and the flexibility of the implant. Second is equivalent or von Mises stress. So it helps to identify the region where the material could potentially fail. And the equivalent elastic strain, which is used to analyze how well the material could elastically deform after absorbing load without permanent damage. So, in order to make this analysis more realistic, we provided a specific patient profile that we considered, and the patient we selected was a 60-year-old female with a 35 kilogram suffering from osteoarthritis and the right hip. And she has a moderate level activity and a reduced bone density, or more known as osteopenia. So, this profile represents a case where we have proper load sharing is critical to avoid further bone weakenings. Right, so the first main two materials used in the initial design is titanium alloy and stainless steel. We picked titanium alloy because it utilizes in orthopedic application due to its exceptional stretch to weight and biocompatibility. And then we used stainless steel, which has high mechanical rigidity, excellent corrosion resistance, and proven reliability in sustaining heavy physiological loads. A comparison is carried out, and the result shows that titanium alloy experience a maximum total deformation about 10.9 mm, while the stainless steel has a lower deformation of around 5.4 mm. And this indicates that the stainless steel is stiffer, whereas the titanium alloy is more controlled flexibility. So in terms of stress, both materials show very similar values, with titanium alloy around 511 megapascal and the stainless steel around 509 megapascal. So in this case, titanium alloy record a higher elastic strain value, meaning it can elastically deform more and absorb load effectively. So this behavior reduces stress shedding and improves load sharing with the surrounding bones. So, taking into consideration of all these problems, we decided to make a minor modification to the design, which we applied aluminum alloy material to the entire hip process design. So, the reason we chose aluminum alloy is because it has low density and high mechanical strength, corrosion resistance. and it has a very good thermal performance, and it's highly suitable for optimization, and it enables weight reduction while maintaining structural integrity and a long-term reliability. So now to compare the results after the modification, for stainless steel, and the total deformation reduced from about 28.8 mm before the modification to 23.2 mm after the modification, showing an improvement of approximately 19%, and has an equivalent stress reduced about 19% and elastic strain reduced by 18%, and this indicates that the improved structural performance after the modification. As for the titanium alloy, the improvement after the modification is way more significant, where the total deformation reduced from approximately 72.4 millimeters to 46.4 millimeters, and this represents a reduction of about 30%, 36%, and the equivalent stress decreased by nearly 32%, and the elastic strain has reduced by around 31%, and this, however, shows that the design modification has a greater positive impact on titanium alloy. So this concludes that the use of aluminium alloy is way more compatible compared to the first two modules that we use. And titanium alloy has a better balance and strength and flexibility, although it deforms more than stainless steel. So it controls the deformation, which allows better load transfer to the bone, and it reduces shielding and supports a very healthier bones response. So this makes titanium alloy more suitable for elderly patients with a reduced bone density. So to conclude this ANSYS software running, so to conclude the ANSYS simulation, the results confirm that the optimized hip prosthesis can safely withstand a psychological loading condition when combined with the patient profile and the material comparison. So the finding shows that the alloy provides superior biomechanical performance after modification, making it more suitable choice for a total hip replacement. Thank you.
In conclusion, this study, an integrated approach, was successfully applied to the design and optimization of a hip prosthesis using 2D drafting, 3D modeling, and material-based optimization. The 2D drawings created in Autocad 2026 provided a clear and accurate dimensions of the prosthesis, geometry, dimensions, designs, and alignment, which served a strong foundation for the overall design. These drawings helped in clearly understanding and shape of the structure of the femoral stem and femoral head before moving into 3D dimensional development. The 3D modeling carried out using Autodesk Inventor enabled detailed visualization for the prosthesis and verification of the component assembly. These steps is ensured that the design closely matched anatomically requirements and was structurally suitable for the future analysis. For the optimization used in our design, the surface modification was not considered and instead material selection was emphasized. Aluminum was our chosen due to its low density and reduced stiffness compared to the titanium alloy and stainless steel. This helped reduce stress shielding, improve load sharing between the implant and bone, and significantly was decreased in the overall weight of the prosthesis. Finally, FEA using ANSYS confirmed that the optimized design could withstand physiological loading conditions with acceptability deformation, stress and strains level. Overall, the combination used to accurate 2D design, detailed 3D modeling, and aluminum-based material optimization resulted a hip prosthesis with improved biomedical compatibility, reduced stress constriction, and better potential for the lifetime performance. This study highlights the effectiveness of computation tools in improving orthopedic implant design. That's all from us. Thank you for listening.